We're going to switch gears here now for a little while. It's going to seem like we're going back to a previous unit, talking about electricity, electric current. Why are we doing that in the context of magnetism as opposed to the context of electricity that we did in our last unit? It's because our last unit was on static electricity, the buildup of electric charge, okay, not current electricity, which is the flow of electric charge. Now, this unit isn't on current electricity either. But in order to do the next concept, which is a magnetism concept, we have to have a little bit of a grasp as to what electric current is. So this isn't the end. Okay, we're not looking at electric current as an end in itself. We're looking at the electric current as a step to do the next major concept within magnetism, which requires us to know a little bit about electric current. Electric current is a flow of electric charge. Specifically, it's the rate of flow of electric charge. How quickly the charges are flowing, not the speed of the charge. Okay, if you're standing on the side of the highway as a police officer with a radar gun, you're measuring the speed of the cars that are going by. That's not analogous to electric current. Okay, the rate of flow of electric charge is not analogous to how fast cars are moving by you, the speed of the cars. Rather, if you're standing on the side of the highway and you got a stopwatch and you're timing and you're counting how many cars are going by per second, how many cars are going by per second, that's analogous to electric current. It's the rate of flow of cars or the rate of flow of charge, not the speed, but the number that are going by per second. Now, because it's the rate of flow, we're going to say it's of charge, that is. We're going to say it's time on the bottom. Anything that's a rate is time on the bottom. Okay? The rate of change of position is velocity. It's d over t. The rate at which work is done is power. It's work over t. Anything that's a rate has time on the bottom. If it's a rate of flow of charge, then it's going to be charge over t. Now, this is the only new symbol that you see here, I. I stands for current. Capital I stands for current. And the units for electric current, the rate of flow of electric charge would be, we got coulombs per second. Oops, almost gave it away there. Did you see that? What's another set of units that would mean the same thing as a coulomb per second? Okay, we haven't learned this, but you have seen it, I promise you, a million times before. What would it be? An ampere, an amp, abbreviated by an A. Okay, so the standard unit is the amp, but it comes from this unit coulombs per second. Usually you see it as amps, but be prepared for coulombs per second as well, because sometimes we do see it that way. Now, let's take a quick look at what seems to be a pretty simple question. It is a pretty simple question. Okay, it is. It says calculate the current in a wire in which 20 coulombs of charge passes in 4 seconds. Again, current is not the speed of the particles. So we're not looking for a distance over time. It's the rate of flow of the particles. Remember, we're standing on the side of the highway, not measuring the speed of the particles or the cars. We're standing on the side of the highway, counting how many cars are going by per second. Well, how many electrons are going by per second? How many coulombs of charge are going by per second? This is our charge. This is our time, right, Wrecker? So we're going to say the current is equal to the charge over the time, which is going to be 20 coulombs divided by 4.00 seconds. We could express that as 5.00 coulombs per second, or we could express that as 5.00 amps. Is that good? Now, that seems like a ridiculously easy question, right? And I'll tell you what, if you get that question and you remember what current is, it is ridiculously easy. Just like we talked about electric potential and potential energy in the last unit, same deal. Okay, the problem is if you get a question like this and you don't remember what current is, then that's a hard question. You got to remember what it is and what equation applies, and then it's easy. Okay, I'm going to give you about 1 minute to see what you can do in these two questions so we can move forward to our last real topic that I want to look at today, which is going to use this stuff as a tool. And that's going to set us up nicely to do our activity tomorrow. If we're okay with that, then I want to move forward here and use that as a tool to study our next thing, which is the analysis of current carrying conductors in magnetic fields. What do I mean by that? What is a current carrying conductor? Generally, a current carrying conductor is a wire with an electric current going through it. That's it. A wire with electrons flowing inside it. Now, it could be something else, right? Air is a conductor when it's moist and lightning forms between the cloud and the ground. That would be a current. It's a movement of charge through a conductor. But generally, it's just going to be a wire that has an electric current going through it. Now, if moving charged particles through magnetic fields experience a magnetic force, it's not going to matter whether they're inside a wire or outside a wire. We've been looking at the hand rule for deflection, studying which way the particles moving through the air are deflected when they're exposed to a magnetic field. But those particles, if they're in a copper wire, are going to be deflected in the same way as they are if they're in air. But this time, just pay attention to this for a second. Just drop your pens just for 1 second. This time, if the electrons are moving through the wire, they can't go in a circle because they're held essentially from going in a circle by the wire itself. So they want to go in a circle, they want to loop around maybe like this, but they can't. But they can experience a force still upwards, downwards, whatever. Let's say they experience a force downwards. They can't leave the wire. So if these particles experience a force downward, then the wire will also experience the force downward. So this time, we're not looking at the path of electrons as a circle. We're looking at what happens to the wire itself as a result of these electrons experience a magnetic force. The wire will experience a force perpendicular to both the field and the direction that the particles are moving. In other words, the direction of the current. It's no different than the charged particles moving through air, except for the fact that the charged particles aren't going in circles now, because they can't. They're held from going in circles by the wire itself. Now, how do we figure out which way the force is? You don't even need to write this part down if you don't want, because in the end, we've already done it. If a particle experiences a force downward by the hand rule for deflection, then the wire will also experience a force downward. If the particle experiences a force upward, then the wire will experience a force upward. We're going to use the hand rule for deflection. Just the same as the particle moving through the air experiences a force in a certain direction, the wire itself will experience a force in the same direction. So for instance, in this case, we're going to say, look, particles going into the page, whether it's in a wire or not, it experiences a force, thumb, fingers, up toward the top of the page. Okay, if the particle experiences that force toward the top of the page, so does the wire, because the wire has to experience a force in the same direction as the particle. How are we going to figure out what the value of the force is? Well, remember, the value of the force on an individual particle is still QVB. It doesn't matter whether it's in the air, whether it's in a wire, whether it's moving through water. The force on an individual particle is still QVB. But what about the force on the wire itself? Okay, the force on the wire, not the force on the particle. Okay, remember, it still applies, although you're not going to use it very often in the context of a wire. If you want to find the force on the particle in the wire or not in the wire, it's QVB. But the force on the wire is ILB. I is going to stand for the electric current in amps. That's why we just spent a few minutes going over electric current, because you're going to need it in this equation. You might even need to find the value of electric current using Q over T, or you might be given the value of the current already. L stands for the length of the wire, or the length of the conductor in the magnetic field. So if you've got, let's say, a wire that's 10 centimeters long, but only 5 centimeters is exposed to the magnetic field, then what length would we use there in that equation? 5 or 10? wire is 10 centimeters long, only 5 centimeters is within the magnetic field, we're going to use 5. It's the part of the wire that's exposed to the magnetic field. And that's going to be measured in meters. And of course, B is the magnetic field strength. And that's going to be measured in Tesla. What's that little upside down T there? You guys know this, right? Perpendicular. Means the wire's got to be perpendicular to the field. In other words, the particles have to be moving perpendicular to the field, of course. Just like when they're moving through the air, they have to be moving perpendicular to the field for this equation and the hand rule to be valid. Let's do a quick example here. 12.4605 says this length of wire, we're going to circle the centimeters because we want it in meters. It's perpendicular to a magnetic field. That's good. All the hand rules we've learned, all the equations that we've learned are valid. Here's the magnetic field strength. Here's the current. We want to find the magnitude and direction of the force. The magnitude is ILB. It's 4.2 times 10 to the minus 3 Tesla. Sorry. No, it's not. It's 2.1 amps times the length of 0.085 times the magnetic field strength of 4.2 times 10 to the minus 3. Whatever that works out to be for the force. Now, for the direction of the force, negative particles, thumb into the page, fingers from north to south, palm points toward the top of the page. So the magnetic force would be toward the top of the page. Is that good? So your homework for tonight is page 601. You've had a chance to work on those questions somewhat already. In addition, I'd like you to work on page 605, these two quick questions, which, as I say, should go pretty quickly for you tonight. Okay?